All right, cool. All right, so determine the inverse Laplace transform of the function below. And they give us the same stuff they always give us, those two tables. So let me just copy it over here. Okay. Yeah, so, first thing that you should do is just kind of open up the initial table that we have, and you're mostly trying to get the denominators to match first, and then you can worry about the numerator after the fact. So right now, s squared plus 2s plus 26, none of these are quadratic when they're written out like this, so we're going to have to complete the square. We'll just go ahead and do that.
That's the easy part for me.
Yeah.
The manipulating other part, that's the more difficult part.
All right, so 1 is going to be our factor. Add it and then subtract it. So now in the denominator, we're going to have s plus 1 squared plus 25. That's kind of nice. At least we get a perfect square there as well. Okay, so now going back over here, just to kind of match it up, it's matching to these, right? The e to the at, either sine t or cosine t, just depending. All right, the other thing that we need to worry about is when we have the s, the e thing multiplied on this side, the right-hand side of the tables over here. So we're just multiplying by an e to the negative as. That's going to be one of these u things. So let me open up the other table. And down here at the bottom. So it's this line right here that we're going to be using. If you have that the Laplace transform has an e to the negative as and then just a normal Laplace transform, it breaks back down to be the function t minus a and then that u thing t minus a. So just to kind of, because I know that looks kind of ugly looking, just to simplify it down, we're going to pull out that e to the negative 5s, and then we're going to be left with s over the s plus 1 squared plus the 25. And now we've broken it down to be an e to the as thing. And then this one now matches, I think it's cosine. Looking back at the other table. We're going to have to play around with it a little bit more, right? Because we also have the s up top. We kind of want it to match one of these, and it doesn't match it yet. So when you just have an s on top, you're going to have to rework it a little bit. So let's force there to be a plus 1 on top so that it matches this on the bottom. All right. So the way we're going to do that, leaving the negative 5s out in front, what I'm going to do is I'm going to add a 1 into this numerator here. That way I get that s plus 1 in the numerator as well as the denominator. But you can't just add a 1 onto it without also subtracting a 1. So to subtract a 1, I'm just going to make a whole new fraction with a negative 1 instead. Okay. Now if I do add these back together, it gets me back to just having an s in the numerator. But now the first term, that's the cosine one here. And then my second fraction, that's the sine one.
Okay.
Now what we also have to worry about is we have to worry about that e thing from the other table.
Yeah.
All right, so when we multiply by that e to the negative as out in front, we don't just get the regular function, we get the function plugging in t minus that a. So we have a 5 as our a up top. So when we do simplify this down, it's going to be whatever the function is at t minus 5 times that u function at t minus 5. That's just using this here. And that's all because of this 5 right here. Now the function that we're talking about, that's the inverse functions that we get from these two. So going back over to the other table, so what we're going to have is that this function, plugging in t minus 5 comes from these two terms, and I'm just going to leave the u t minus 5 on the back end. So this first one, that was the cosine one here, where the a is a negative 1, and then the b is going to be 5. But we have to be careful, because when we do substitute it in, all of the t's that we have to replace with t minus 5. So it's going to be e to the negative 1 t minus 5. And then cosine of b, which is 5, times t minus 5. That minus, and then this one's the sine one. So the same thing, e to the negative 1 t minus 5. And then sine of 5 times t minus 5. And then that should really be it. I mean, you can simplify these down a little bit, but that's the final answer. Distributing the negative 1, distributing the 5 into this.
And could you go back to the other Laplace for the transform table?
Yep.
So the smaller f, I'm trying to distinguish the function between the smaller f and the larger f. The larger f is the one that's multiplied times e to the negative st.
Yeah, so this parentheses here, that's the large f. Anytime you have s's in there, it's the large f. This is already after you've taken the Laplace transform. We want to get it from this back to just functions of t, which is the normal function, the little f.
Okay, that makes sense. Okay.
Just to type it in to see if we did get the right answer. So it's going to be e to the negative t plus 5 cosine of 5t minus 25 minus e to the negative t plus 5 sine of 5t minus 25. And then that whole thing times that u function, t minus 5.
Did you forget the parentheses around the t thing?
Did I?
Like, they care about that. I don't know why. No?
No, I don't think so.
Oh, because you multiplied it through, I see. That's why. I don't know.
I'm not sure either. Let's see what the right answer is. Oh, it changed my numbers when I hit that button. Oh,
okay.
no. Alright, sorry. I didn't realize it was going to change the numbers for me, but it did.
No, it's okay.
I mean, it's in the format, right, that we have? It is the right format. I must have just had like a negative sign in the wrong spot, or who knows. But it's the right answer for the question that we were doing.
And then try to debate whether I should. It's in the same section, in the number 8.
Okay. All right. So solve.
You already did it, huh? Just have to probably go through.
Oh no, I think it's just because I have this thing clicked up top.
Oh, okay. Oh, that teacher edition.
Yeah. I don't. Maybe we did go through this one. I don't think so. We'll just go through it anyway. All right, so it's the y double prime plus y is the u t minus 2 and initial conditions y of 0 is 0, y prime of 0 is 3. All right, you do the same thing here that we were doing with the other equations with the Laplace transform, is we want to take the Laplace of everything. So we're going to take the Laplace of the second derivative there, plus the Laplace of just the function y, and that's going to be equal to the Laplace of this u function. Okay, I hope that you've been doing this so much now.
It's like
yeah.
clockwork.
So when you have this, the second derivative, that's this line. So it's going to be s squared, and then times the Laplace of y. That's going to be minus s, and then the function at 0, which is 0, minus the derivative of the function at 0, which is 3, plus we have the Laplace of y. And then the only new stuff from section 5 was this, when we have the Laplace of that u function. So that, again, is coming from this line down here. Or I guess this bottom line works maybe a little bit easier and better. I don't think it's going to matter for this one, because it'll be the same thing. So anytime you're taking the Laplace of a function like this, you want to think of what's in front of it, and what we have in front of this is just the number 1. So what that means, because my a in this case is going to be a 2, is that whenever you have a function and then that u function out in front, you're going to get an e to the negative as from the a and the u, and then just whatever the Laplace transform is of the function out in front. So to break it down into steps, we're going to have the e to the negative 2s out in front, that's coming from the 2 here, and then times the Laplace transform of what's in front of the u, but what's in front of the u is just a 1. From the other table, we know what the Laplace transform of 1 is. It's just 1 over s. All right, so all that happens when you have these u's is it includes an e to the negative whatever s out in front.
Okay.
You do just have to be a little bit careful about the minus stuff. We didn't have to worry about it in this case because the function out in front didn't even have any t's in it. But if it did have t's in it, you just have to be a little bit careful about which one you'd be doing. This line, if you had the t minus a into it, this line down here, if it was just a normal function g of t, and it would come out to be this. So you would have to shift your a's if there was, not your a's, sorry, shift your t's if there were any t's in the function. All right, but now we just keep going. So this is going to, bringing the Laplace transform together, we have an s squared and then plus a 1 times the Laplace of y. That's coming from this term and this term. On the right-hand side, we have that e to the negative 2s over s, and I'm also going to be adding this 3 over. Remember, this was just 0 here. All right, combining these terms together. You have to get like terms, and it's not hard. They would combine together to be that, right? Just multiplying the 3 top and bottom by that s. Okay, and now we can divide over by that s squared plus 1. Okay. So we're here. The Laplace transform is what it was already on the right-hand side, and now we're dividing by the s squared plus 1. All right, now let's see what it's asking for. Yeah, it wants the actual solution. So we do have to find the inverse of this. We did just practice it in the last example, so that's nice. Whenever you have something like this, you want to break it down to have anything that's multiplied by the e separate from anything that's not multiplied by the e. So I'm going to separate this out to be e to the negative 2s over that denominator plus the 3s over that denominator. Oops.
we just have to do partial fractions.
And now we're going to have to do partial fractions, but we're actually going to have to do it twice. We're going to have to do it for this one after we factor the e out, and we're going to have to do it for this one.
Oh, is that why it's just the 1 up top when you factor out the e?
Yeah, so when you factor out the e, there's just a 1 that's going to be left up top here.
Oh, okay. That makes sense.
Keep deleting stuff as I'm typing. Yeah, and so unfortunately, partial fractions for both of these. The partial fractions for the one that has the 1 on top, and the partial fractions for the one that has the 3s on top. What is a little bit nice is that when you do both the partial fractions, the right-hand side is going to be the same regardless. So let's look at that first one. We cannot factor that any further, and we have the linear term s, and then we have that irreducible quadratic term. So we're going to have a fraction over the s, plus we're going to have a linear fraction over the s squared plus 1. So that's just the partial fraction decomposition. Multiplying both sides by that denominator, we're going to end up with just a 1 on the left, and then a times s squared plus 1 plus that bs plus c times just s. Multiplying it all out. And then solve for the a, the b's, and the c's however you like to solve for it. I usually do the coefficient thing. So we have s squareds floating around, 0 on the left, and then a plus b on the right. We have s's floating around, 0 on the left, and then just a c on the right. And then we have constants floating around, a 1 on the left and an a on the right. So pretty easy to solve this one. We get the a for free is 1, we get the c for free is 0, and then if the a is 1, that says that my b has to be negative 1. So wherever you want to write this now, but this we have now done the partial fraction decomposition for. That is going to be 1 over s plus negative 1 over that s squared plus 1. All right, but we also have to do the partial fraction decomposition for the other one, the one that had the 3s on top. So what I was saying is kind of nice is that without doing any work, I'm just going to set the 3s from this numerator here equal to this right-hand side that we already had. The as squared plus a plus bs squared plus cs. Because the right-hand side is not going to change. It's still the same stuff. But now the a, the b, and the c are all going to be different because the left-hand side is different. So again, we have s squareds, 0 on the left, a plus b on the right. We have s's, 3 on the left, c on the right, constants, 0 on the left, a on the right. So this one gives me that my a is 0, which means that my b also has to be 0, and I only get the 3. So this one didn't even really seem like it was worth it. Oh yeah, I'm dumb. I don't even know why we did all that, right? Because there's an s up top here and an s down here. We could have just canceled them out. Sorry, a little waste of time.
It's okay.
All right, but that means that we can go back to that Laplace transform and then write it so that it's all broken down. For that first term, we still have that e, the e to the negative 2s that's sitting out in front. But now the partial fraction decomposition for it, we wrote down here. So I'm going to put that there. Plus, the other one, we had just the 3 over the s squared plus 1 that did not have the e on it. Now going back to my table, we would just pick out the ones from the table that matched these in the correct form. So the first one, just the 1 over s, that's the one that's just the 1. negative 1 over s squared plus 1. That looks like a sine thing where you pull the negative 1 out, and then it's just that 1 over s squared plus 1. And then this last one's the same thing. It's going to be another sine one, but after pulling the 3 out. Where you do need to be careful is you need to be careful about this e out in front, because this e out in front is going to be that u function again. And we have to be careful about making sure we shift the t's in the right locations. Okay, so let's do that, right? Let's leave that alone, because we don't really know what this is going to be yet perfectly. But what I do know is that this e to the negative 2s is going to be a u times t minus 2. So that's coming from this other thing over here. Right, this down here. Now, when I do find whatever the inverse Laplace of this stuff is, I need to make sure I substitute in t minus 2's into that inverse. That is not going to be the case for this one, though. This one is just whatever that inverse is. I'll just to give it a different name, g of t. All right, so does that make sense there? Why we have to do it like that?
That makes sense, yes.
Okay, so now just to do it, so going back to the other table, we already said that the inverse Laplace of 1 over s is just 1. After pulling this negative 1 out here, this was sine of just t. But we have to be careful, because we can't just plug in a t there. We have to substitute in that t minus 2. That was times the u, t minus 2, plus, and then this last term, we pulled the 3 out, and then it was just a sine of t again. Do not have to substitute in the t minus 2 into this one, because this one did not have that e multiplied out in front. All right, so just to see if it works, oh, darn it. Did I type something in funny again? I don't think so. I think I just goofed up somewhere. I'm not really sure.
I don't see it. If you did, 1 minus sine t. Is it? You did put the negative, so I don't know.
Well, let's just see what the right answer is again. Oh, it says it was a cosine instead of a sine. Oh, I see where my mistake was. It was back here with the partial fractions. So the b was negative 1, and the b had the s on it. So that should not have been a negative 1. That should have been a negative s here. So now going back down here, this should have been a negative s, which means that instead of the sine 1, it should have been the cosine 1 instead, the one that has the s up in the numerator. So this should be 1 minus cosine of t minus 2 there. Oops. But now that we have that, it is asking for what the graph is going to look like. And that's not easy to visualize what that's going to be. Remember that this u function, what the u function does is that anything multiplied onto the u function doesn't turn on until it reaches that number 2. So this graph is just going to start off as the graph 3 sine t, and then when it reaches that value 2, this is going to start working and it's going to change. So we just have to pick the graph that starts off as 3 sine t. After that, it can do all kinds of crazy stuff. So it's definitely not A, because that's just a flat line at the beginning. This one looks promising, but I'm a little bit worried about how big it jumps up. Right, if that's 8, like this is jumping up to 3, but at the value 2, I don't know, it just looks kind of weird to me. Well, maybe. We'll come back to that one. Can't be C, right, because C does not start off as 3 sine t because it's starting up, where 3 sine t starts at 0. It looks like D's doing the same thing, right? It's not starting at 0. Okay, I changed my mind about B. It's got to be B. It starts off as 3 sine t, and then this function kicks in at 2, and then it does some weird stuff after that. Okay. Yeah, so sorry about that one little mishap there, but other than that, we did it right.
That's my whole life. And then I just had one more question on 7.7.
Okay.
Either 4 or 5. It doesn't matter which one. I still have to do both of those.
Okay. Determine the Laplace of f where the periodic function is described by its graph. Okay, so we have this graph, this periodic graph that's going, and we want to know what the Laplace is if this is my function. So what you need to do for examples like this is figure out what that function is in periodic form. This is just straight lines, right? Where after it goes to the right 3a, it goes up 3. So we can find the slope for that, right? Up 3 over 3a. This is going to have a slope of just 1 over a. I guess to really write it out, it's going up 3 over 3a, and then the 3's cancel, so we get a slope of 1 over a. It also has a y-intercept at 0. So that means that the equation for this function, this straight line, is just going to be y equals 1 over ax. Now that's the equation of this one. The problem, right, is that it's periodic, which means it does that and then it repeats forever and ever and ever. And I don't know if there was like a really good way of writing that out. Let's see what we wrote, or what I wrote in my thing. Yeah, we didn't really have like a nice way of writing out when something was periodic. So let's just say that's the equation with period 3a. Every units of 3a, this just repeats itself forever and ever and ever. All right, is that part okay, finding that equation with the period? It's just the straight line. All right, from here, now we want to find the Laplace. Now, whenever you're finding the Laplace of a periodic function, there's a formula to it. And this is the formula. So this is just coming out of the book. The Laplace transform is the Laplace transform of the periodic function divided by 1 minus e to the negative st, where that capital T is the period. And also where this part, the Laplace of the periodic function, we get this by integrating just from 0 to the first period of e to the negative st times our function. Remember, this was the original definition of the Laplace transform, the integral of that e to the negative st times the function. That's coming from like section 2, I think.
I remember that.
All right, so we just have to do it. So let's find just this numerator part first, the Laplace of just the one period. That we're going to integrate starting from 0 to 3a over this first period. E to the negative st, that's just a staple for the Laplace transform. And then the function itself, remember we decided was 1 over a. We need to put a t in there, not an x. That should be y equals 1 over at instead of an x there. It doesn't really matter, but just for this part. All right, and then we just do this integral. We can pull the 1 over a out to the front of the integral. But then we still have the 1 from 0 to 3. We still have a t, and we still have an e to the negative st. All right, and maybe it's been a while since we've done integrals like this, but we have a tool for ones like that, and that's that integration by parts. So we're going to have to set a u. I'll just set the u to be t. We're going to set a dv. The dv I'll let be that e to the negative st. From here, we have to find a du, which would just be dt, and then a v, which is negative 1 over s e to the negative st. Plugging that in. We still have the 1 over a out in front. And then the integration by parts is u times v, so negative t over s e to the negative st, minus the integral of v du. So just negative 1 over s e to the negative st dt. All right, just continuing it on, just to leave this term alone, the negative t over s e to the negative st. Here, my double negatives cancel out. I have a 1 over s, but then the antiderivative of this is going to bring down another negative 1 over s. So we get negative 1 over s squared e to the negative st. And then we're going to evaluate that between 0 and then the upper limit, which was 3a. In fact, that should be a 3a there as well. The variable that we're integrating over is t, so we're only plugging in 3a and 0 into the t's. Plugging 3a into the t's, I get negative 3a over s, e to the negative s times 3a, minus 1 over s squared, e to the negative s times 3a. And that's going to be minus, plugging 0 in for the t's. This first term is just 0, that's nothing. But this term is going to give me something. The e to the 0 is just 1, so we're still going to get that coefficient negative 1 over s squared. Yeah, we could try cleaning this up. So they all have a 1 over a. I guess I'll just leave that out front for now. I don't know if there's really going to be much that we can clean up here. I didn't do what I wanted it to do. And then we have a... Yeah, it's the thing on the end. Plus 1 over a squared, I guess. Just leave it like that. Yeah, so there's nothing we can combine together here, really. It's just all kind of gross and ugly. And it's only going to get worse, because this was just the numerator. Now I have to take that and divide it by this 1 minus e to the negative st, where that t is the period 3a. So this thing divided by 1 minus e to the 3as again. So I wouldn't bother trying to simplify that, because it would just be gross. I would just write it like that in the program here. So 1 over a, negative 3a over s, e to the negative 3as minus 1 over s squared. I guess I can just throw the e right onto that. That all plus 1 over as squared. And then that whole thing divided by 1 minus e to the negative 3as. Oh, we've gotten so many wrong today. I mean, I know it's the right answer. It's just the simplifying stuff.
Was there any way to use like the formulas that they have, or is the only way to do this one is by integration?
The only way to do these periodic ones is by integrating. You cannot use that table for any of these. I was hoping there would be an easy way to simplify it down, but I don't know. I mean, we can just get the right answer again, but it's going to look nothing like this because it's not simplified.
Right.
We'll just get to it and then we'll work backwards. Okay, so this is the right answer, right? And this is what we got. I promise you that if you simplify this thing down, unless we were slightly off, it would simplify down to be this thing.
It is just going to be an ugly answer then.
It's going to be an ugly answer regardless, even after simplifying it down. I mean, I can kind of show you a little bit of what they do here. Maybe we can find our mistake as we do it. So just distributing the 1 over a into the parentheses is going to cancel out the a with the first term, and we're just going to add an a over here. I'll also go ahead and divide by that other thing. So in the numerator, we have negative 3 over s e to the negative 3as minus the 1 over as squared e to the negative 3as plus a 1 over as squared. That all divided by the 1 minus e to the negative 3as. Okay, so to get from here to what they got, it looks like they break it up as much as they can. So to do that, trying to think of the best way to do it. Somehow I got it in the denominator. It's not supposed to be there. There's the mistake right there. When we were plugging 3a into this, I don't know why that e went to the denominator. That must have just been a typing mistake. But that should be up here in the numerator instead.
Okay.
So that should be in the numerator. That's why it counted it wrong for us. This should be in the numerator. If I had typed it in like this, I promise you it would have counted it right. So that must have just been a computer thing. We didn't make any mistakes, which is good news. All right, from there, you would just combine like terms together, and I don't really feel like doing it. I promise if you type it in.
I don't blame you.
If you type that in, it will count it right.
Okay.
Or for whatever your numbers may be.
All right, yeah, I'm just going to have to go back and work in and see if I can. I'm going to have to integrate it. All right.
For number 5 here, you don't have to go through this one if you don't want to, but it's the same kind of thing, right? You'd want to come up with a function that's periodic and then just go from there. Do you want to go through it, or are you sick of it?
I'm going to have to go through it eventually. We can. I mean, if you want to, we have time. But
We could try it, because this one looks hard to me.
Oh, man.
So it looks hard because it looks like two separate functions that repeat forever and ever and ever. And I don't know the best way to do this one. There's probably many ways to do it, But one of them's got to be easier than the other. I know it's an absolute value function. It's just that I don't think we can do absolute values with the Laplace transforms, because we don't know what the Laplace transform of the absolute value is. Another thing that we could try is we could try to do this using those U's, but that seems gross.
That's what I was trying to do. That's what I did for the first 3. I was able to get away with that, but when I got to these, and I was like, I don't know how to do it.
Maybe we could do here, because this is going to have a slope of going up 9 over 3a, so it's going to have a slope of 3 over a, t. So that's this first diagonal line. Plus, now what I'm going to do is I'm going to add on a u function that only starts at 3a. I might have to get back to you on this one after I work on it for a while.
Okay.
I don't want to just sit here and get the wrong answer over and over.
That's fine. You could just shoot it out in an email or something whenever.
Yeah, I'm going to have to.
Yeah, because I'll probably still be doing homework or finishing those last couple of problems that I need to do.
Okay. I'll email out the solution to this one then. I'll just have to think on it for a minute.
Okay, sounds good, Mr. Lisa. Thank you.
Yeah, of course. Thanks for coming.
No problem. Have a good one.
Thanks, you too.